Welcome to the video lecture on the course ARM Microcontroller and Embedded System, Module 3, Embedded System Components. I myself, Professor Shilpa Biradar, Assistant Professor, ENC Department, Guru Nanak Dev Engineering College, Bidar. In the lecture 1, we have seen what is an embedded system, what is the purpose of an embedded system, how the embedded systems are classified, and what are the basic application areas of embedded systems. Now, in the lecture 2, we will see how the embedded systems are built and what are the elements required to build an embedded system. This diagram, it gives an embedded system. So embedded system actually it is made of system core, memory, ports or the actuators or the input ports or the sensors and other supporting ICs and subsystems. And the main part of embedded system, that is system core and memory, and we have a communication interface to the external world. So let us see what are the core elements of an embedded system. The core of an embedded system falls into following categories, that is general purpose and domain specific processors, programmable logic devices PLDs, application specific integrated circuits ASICs, commercial off the shelf components COTS. General purpose and domain specific processors falls under microprocessor, microcontrollers, digital signal processors. Microprocessor is nothing but a central processing unit which is capable of performing arithmetic as well as logic operations according to the predefined instructions. In general, CPU contains ALU and CU and working registers. Microprocessor is dependent unit and it requires other devices like memory, timer unit and interrupt controller, many other external devices to be connected for the microprocessor. Microprocessor is just a CPU which is capable of performing arithmetic and logical operations. The first microprocessor was Intel 4004, a 4-bit processor which was released in 1971. What is microcontroller? So microcontroller is nothing but in general it is defined as system on a chip SoC. When you compare microcontroller with a microprocessor, the microcontroller as the name system on chip, it is having inbuilt RAM, ROM, flash memory for program storage, timers and interrupt control units and dedicated output input ports. Microcontrollers can be considered as a superset of microprocessors since microcontrollers contain all the necessary functional blocks for independent working. They form greater place in the embedded systems. All the nowadays, whatever we have the embedded systems, we have seen in the last lecture, that is application areas of embedded systems. All the embedded systems are built with the microcontrollers. So the heart of embedded system is as microcontroller or the microprocessors. Microcontrollers are cheap, cost effective and are readily available in the market. So these microcontrollers are general purpose or application specific, or it can be designed specifically for automotive applications. Since microcontroller contains all the functional blocks like memory, RAM, ROM, flash memory, timers on inbuilt on the chip. Digital signal processors, that is DSPs. Digital DSPs are 2 to 3 times faster than general purpose microprocessors in signal processing applications. DSP can be viewed as a microchip designed for performing high-speed computational operations for addition, subtraction. When the high-speed performance is required, then we should go for the digital signal processors. DSPs incorporate the following key units, that is program memory, data memory, computational engine, I/O unit. Audio video signal processing, telecommunication and multimedia applications are typical examples where DSP is employed. Next we'll see big endian versus little endian processes. So what actually mean endian? Endianness specifies the order in which the data is stored in the memory by processor operations in a multi-byte system. Suppose the word length is of 2 bytes, then data can be stored in memory in two different ways. Higher order of the data byte at the higher memory and the lower order of data byte at the location just below the higher memory. So these big Indian and little Indian. So Indian processors, they are again categorized as little Indian and big Indian. Little Indian means the lower order byte of the data is stored in memory at the lowest address. We can see the next slide. So big, this is a big Indian, little Indian processors. If you see the little Indian operation, so little Indian means the lower order byte of the data is stored in memory at the lowest address and the higher order byte at the highest address. So if you see this diagram, so this little Indian operation, so it is divided by 0, byte 1, byte 2, byte 3. Byte is nothing but the 8 bit, that is 4 into 8 is 32. So base address, so the lower byte is saved in lower memory address, and you can see the byte 0 is saved in 2000, that is 20,000 base address. The next byte is saved in next higher location, the next byte is saved in next higher location, and the third, that is last byte, is saved in the higher location. So let us see what is big Indian operation. So big Indian means the higher order byte of the data is stored in memory at the lowest address. It is opposite to the little Indian, that is higher order byte is saved at lowest address. So if you see this diagram, that is byte 3, as the data is divided by 0, byte 1, byte 2, byte 3. So byte 3 is saved at lower address, that is 20,000, and byte 2 is saved at 2001. So byte 0 is started at the higher address. Now, how the load, store, operation and instruction pipelining is done in the processors or the controller. So already there is processor, the reduced instruction set processor is orthogonal and it operates on registers. So reduced instruction set. The instruction stores data from a specified register to a specified memory location. So let us see how load store operations are done in a processor or a controller. So we can see this load store operation. Just simple example, load r1 comma x. There are three variables x, y, z. So x is having some value, that is you can see here 007f23. So load r1 comma x, some small program is written. So load r1 comma x, load r2 comma y, add r3, r1, r2. So what actually it is, how it is load and how it is stored operation is done in the processor or a controller. So load R1 means the value of X, that is it is loaded into the register R1, and Y is loaded into R2, and add R1 and R2, and that the result is saved in the register R3. So R3 is the destination, then this again store. So what we are doing, so storing the content of R3, that is sum of both R1 and R2 into the location Z. So if you see this small program, the how it is internally in the processor or the controller it is done. So X is pointing to 00 and Y is pointing to 7F and Z is address location 23. So you can see the steps also 1, 2. The first step is it will load the X into the R1, and second, that is the Y is loaded into R2. So what is, this is your first step and second step. And third step, you can see here the R1 value and the R2 value is given to the arithmetic logic unit, that is ALU. This it will perform the arithmetic operations, that is as we have used add instruction. So the contents of both R1 and R2 are added and it is given to the register R3. So after this step, so what is done, thus it will store R3 again into the Z. So this is the last, you can see the content of addition of both R1 and R2, it is again saved back into memory location pointed by Z. So this is how a simple load store operation is performed in the processor or the controller. So next we'll see what is instruction pipelining. So as we heard how the instructions are executed, so how the instructions are fetched and how they are decoded. So just if you see this diagram, so this is a single stage pipelining concept. So to execute any instructions, there will be many number of stages of pipelining. So just we'll see what is stage, that is single stage pipelining, how the pipelining is done. So if you see here, always we have in the processor and controllers, that is clock pulses. So machine cycle 1 fetch PC. PC is a program counter. So program counter holds the address of next instruction to be executed. So execute PC minus 1. So if you see this diagram, so program counter, so how the pipelining is done. So the fetch part fetches the instruction from the program memory or code memory, and decode part decodes the instruction to generate the necessary control signal. So when clock pulses in the first machine cycle fetch the program counter, it will fetch the address, then execute PC minus 1. So that's why I told program counter holds the address of next instruction to be executed. So if you see in the second, see fetch is program counter plus 1, it will execute the PC. So it will fetch the next instruction which holds the next instruction of to be executed, and it will execute the PC. In the next step, it will be fetch PC plus 2, that is program counter is incremented by 2, and but it will be executing program counter plus 1. In this way, the instructions are fetched, decode and executed in a sequence. This is called as instruction pipelining. The another core element, so the system core is programmable logic devices. So already you have seen what is logic devices. Logic devices provide specific functions including device-to-device interfacing, data communication, signal processing, data display, control operations. Almost every other function a system must perform. Logic design, that is logic devices, can be classified into two broad categories, fixed and programmable. The circuits in a fixed logic device are permanent and they perform one set of functions. PLDs are based on rewritable memory technology and the device is reprogrammed to change the design. Programmable logic devices, that is PLDs, again they are classified as CPLDs and FPGAs. FPGAs abbreviated as field programmable gate arrays and complex programmable logic devices. So FPGAs are used in a wide variety of applications ranging from data processing and storage to instrumentation, telecommunication and digital signal processing. So FPGAs offers the highest amount of logic density, the most features and highest performance, whereas CPLDs offer very predictable timing characteristics and therefore ideal for critical control applications. So CPLDs by contrast have much smaller amounts of logic gates, that is up to 10,000 gates. The examples of CPLDs, Xilinx School Runner, an example, which are very inexpensive, making them ideal for the cost-sensitive, battery-operated portable applications such as mobile phones and digital handheld assistants. Application next, the another part of system code, that is application-specific integrated circuit, that is called ASIC. This ASIC is a microchip designed to perform a specific or unique application. It is used as replacement to conventional general purpose logic chips. So we have seen at the digital camera. So digital camera is a best example of embedded system. So digital camera, it will do only the specific task, that is capturing the pictures or storage. So it will not do any other task. So that is called as application specific integrated circuit. So ASIC integrates several functions into single chip and thereby reduces the system development cost. ASICs can be prefabricated for a special application or it can be custom fabricated by using the components from reusable building block libraries. We see the last, that is commercial off the shelf components, COTS. So this is again a part of system core. We are seeing with the system core. So this commercial off the shelf COTS product is one which is used as is. You can see this sentence, that is COTS product is one which is used as is. Our design COTS are products are designed in such a way to provide easy integration and interoperability with existing system components. So examples of like remote control toy car control unit including RF circuitry part. So this is the best example for the COTS. So it will be operated, which is used as it is. So as it is there. The major advantage of using COTS is that they are readily available in the market, cheap, and developer can cut down his or her development time to great extent. A COTS component in turn contains a general purpose processes or application as instruction set processes or application specific ASICs or application specific standard product or programmable logic devices. So you can see COTS is built with all general or it may be built with the processes or it may be built with an ASICs or it may be ASIP, that is specific instruction set processes, or it may be built with the PLDs. So in the next lecture, we'll see what is the memory and what is the communication interface, how the embedded system are interface with the communication interface.